All right, I think everyone made it back, right? Yeah. Okay. I think we're ready to start when you are, Eric.
Awesome, cool. Well then, in that case, I'll get started here. Um, so for for everybody who doesn't know me, my name is Eric Johnson. I helped found TAR back in 2017. I was the initial president. I was the president from the beginning of 2017 till the end of the 2018 school year. Um, And so after I did TAR, I started the YouTube channel Intelligent Quads based off of a lot of the things that I had learned um, while being in TAR, and trying to like teach a lot of the things that I'd seen members like struggle with, namely Gazebo and installing all the open source drone packages. Um, then I also got hired at Bell Helicopter, and I've worked there for a little over 4 years now. I worked 2.5 years on the Bell autonomous pod transport. And there I was primarily doing hardware in the loop software testing. So I was in charge of maintaining a computer where I was writing emulators of the different sensors and actuators communication protocols. And that was actually directly plugged into our FCC. And I was able to um, inject failures at a communication protocol level so that we could test our drivers and make sure that the system would gracefully handle faults. Um, then after APT, I worked another year on another drone project that I can't really talk too much about. And then I'm also working on a different drone project that just started um, that I also can't talk too much about. Um, so with the background out of the way, we can get started with the presentation. Um, so the agenda for the presentation is I'm going to give a brief overview of a unmanned aerial system, and that'll be in the form of a presentation. Hopefully this will take about 30 minutes, and then I'm going to do a brief demonstration, which y'all should also be able to do it at the same time that I'm doing this. And then that demonstration will be showing off how PX4 and QGroundControl interact, and then I'm going to do just a brief demonstration of how you can write software and test it using the Intelligent Quad Simulator. And then I'm going to try to keep that around 5 to 10 minutes, and then I'll have a Q&A session. So hopefully the whole presentation will take about an hour. So getting into what an unmanned aerial system is composed of, there are typically three computers that compose a UAS system. There is usually the flight computer, which runs your control loops and the Autopilot software. And then there's a ground control station that usually runs on a laptop and then has a data link to the flight computer. And then a lot of times there is a third computer, which is the companion computer, which houses more mission specific software, and communicates directly to the flight computer and gives more high level commands such as waypoints and velocity commands. This is what a typical drone that 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 I've made at TAR in the past kind of looked like. So we had the Jetson TX2 as our companion computer, which talked directly to the Pixhawk 2. And then the Pixhawk 2 had some external sensors, which was like a 1D LiDAR for altitude estimation, or like a GPS if we were flying outside. The Autopilot board also had some internal sensors, so it has a IMU and a gyro, as well as a lot of ports to plug in other external sensors and radios and stuff. And then we also had the SICK radios, which plugged into the Pixhawk and then to the laptop, which allowed you to command and monitor the system. And then over here on the left, we had more mission-specific sensors such as cameras and LiDARs that talk directly to the companion computer. So now I'm going to go a little bit more in depth into how the software on each of these computers are structured. So the Autopilot, as I alluded to before, runs the control loops. It also has a communication interface. It has a logging module, and then it also has drivers for all your sensors and actuators, as well as anything that directly comes with the flight control board. And then another thing that's pretty special about the Autopilot is that it runs a real-time operating system, which basically ensures that all of the software tasks are scheduled frame by frame, and the operating system ensures that every task runs in a given amount of time and has the proper amount of allocation to run per frame. So this is kind of a block diagram of how an autopilot is set up. This is some of the modules. It's not like a complete set, but this is both how more or less how PX4 and Ardupilot are laid out. So you basically have all your drivers, which interface with hardware, and each piece of hardware gets its own driver, and then they communicate over an abstraction layer that basically takes whatever specific protocol and then puts it into a common protocol for like a gyro or a GPS, and then it gets routed to the different modules that'll consume the data. So for instance, like your sensors will then go to what is called an extended Kalman filter, which basically takes all of the sensor data, and tries to filter it and make a more accurate estimate of the state of the aircraft. And once the state of the aircraft is formulated, that data gets passed over the control loops, and then the control loops basically take the desired state of the aircraft and calculate what kind of inputs need to be given to the actuators to reach the desired based off of the current state. And then there's also MAVlink, which is the communication protocol that most open source drones use. And then usually there's a logging module that is also part of the Autopilot software stack. So I briefly wanted to talk about more or less how the control loops work on a drone. So drone software uses what is called a layered PID system, where the output of one PID controller goes in as an input to the next PID controller, and there are typically 4 layers of PID control in order to control for position. And there are also 4 layers. There are 4 layers of PID, and then there are 3 axes of the layered PID control. So what I'm showing here is one axis. This would be the roll axis. The yaw axis would have the equivalent, but different gains and different inputs for that axis. So basically, like, say we want to go to a commanded position. Basically, the commanded position will be input here, and then the current position will be subtracted, which will basically give you an error, which then you'll have a P and an I and a D term, which I don't want to go too in depth into this, but basically those terms will then get summed together, and then that'll become the input here, and then so on and down the mix. One thing to keep in mind is typically the only one that is a full PID controller is this rate mode, but PX4 and Ardupilot work a little different, so I just put the PIDs across all of them. I know that in Ardupilot there's a PID controller here, and then there's only a P controller, and then also only a P controller for velocity, and then also only a P controller for position, which then trickles down into motor commands. So now I'm going to give a brief overview of how how typical autonomy stacks are laid out for drones. So autonomy software is basically any software that is mission specific and does not need to run in real time. So because it doesn't have the real time requirement, it doesn't have to run on the Autopilot, which is running a real time OS. It can run on a different computer, which we call a companion computer. And this typically runs Linux. And usually these autonomy stacks are comprised of multiple modules that communicate on some middleware, which for open source drones, that middleware is usually ROS. And ROS is great because there's a lot of open source modules that you can just download and then integrate into your system. And you don't have to do a lot of work to essentially get the inputs and outputs working with your system. So here's an example block diagram of how the structure of an autonomy stack for an open source drone might be. So you'll have modules that are in charge of interacting with hardware. So a lot of times, like you'll have like a LiDAR module, which will be set up to talk the specific protocol for the LiDAR, and then it'll take the LiDAR data and then create ROS messages, which any of the ROS nodes can subscribe to. And similarly, if the camera, it'll talk whatever protocol the camera wants and then put that onto the ROS network as the essentially image message that any of these nodes can subscribe to. One thing to note about this is MAVROS and MAVlink. This is how the autonomy will talk to the Autopilot. So MAVlink is hold up. I'll talk about MAVlink in a second, but essentially MAVlink is a communication protocol that open source drones use to communicate both between the companion computer and also to the ground control station. MAVROS is essentially taking the MAVlink data and then translating that data into ROS messages, which all of these nodes can subscribe to. So the structure of this is an example, but this is how I would encourage you guys to think of and set up your autonomy suite for whatever mission you guys end up deciding to do. So a lot of times, like you'll have like a SLAM module, which can use LiDAR camera data, and then that'll help like estimate position, which then you can give that position estimate to MAVROS, which can be sent over to the Autopilot, which then can also be fused into the extended Kalman filter with all the other onboard sensor data on the Autopilot, which can help you, especially in situations where you don't have GPS and you need to use something more advanced, such as SLAM. A lot of other times, some of the other things that you might want to do with your drone are like recognize objects. So you can use open source like machine learning software like YOLO, which you can like train it to recognize different objects. And then I would encourage you guys to make a server, which any of your other behavior modules can contact and request data, whether that be maybe an occupancy grid or the positions of objects, or maybe even the positions of other vehicles if you have a multi-vehicle situation. And then I would also encourage you to put your behaviors into separate ROS nodes. That way it's just a little bit more modular. And then I would recommend that you create a flight vehicle manager, which basically will be in charge of managing which behavior is currently allowed to publish to the Autopilot, and essentially creating one interface that will publish the Autopilot. One of the pitfalls that I've seen in the past is like when you have a bunch of different behaviors, everybody can just publish waypoints onto the ROS network, and sometimes there's no clear definition of who's in control, which can lead to a lot of confusion. So now a brief overview of what the ground control station does. So the ground control station is a graphical user interface for the operator of the unmanned aerial system. So it'll show you usually a map with the position of the drone, the orientation, and some telemetry data to help you monitor your autopilot. It will also allow you to change parameters, and there are a lot of parameters in PX4. So it's nice to have a user interface that also has the description, and you can go in there and manage your system. You can also conduct mission planning if you choose to do that. And those are essentially the general functions of the ground control station software. So now a brief overview of MAVlink. So I like to think of MAVlink as the glue that allows all the different computers in your system to communicate. It's a very efficient communication protocol because it's designed to essentially be sent out on a radio where you probably won't have a lot of bandwidth because you're taking like a little radio with you out to the field, and the drone only has a little radio, and usually the ground control station only has a little radio, so there's only so much data that you can get between them, especially if you start going to long distances. So MAVlink has been designed to use as much or as little data over the wire as possible. So this is what a typical MAVlink message would look like. So you would have something signaling the beginning of the message, then you would have the length of the payload, then you would have a sequence. So this is basically like whoever's publishing this is like saying, oh yeah, this one was published in this order. And then the system ID and the component ID. So this basically tells you which system this MAVlink message is being sent to, and also the component of the target system that this message is meant for. And then there's also the message ID, which then corresponds to the definition of the data, which both systems will have the definition. So the sending system will basically fill out maybe something that looks like this, and then the receiving system will take this data and then decode it, and then it can use it in the different functions that it needs. And then finally, there's a checksum, which basically this is an algorithm that is run over all the data, which ensures the integrity of the message. So if there's any noise that the radios pick up, it can verify that the message has been corrupted using this checksum. And another thing to note about MAVlink is that both PX4 and Ardupilot use MAVlink. However, they don't use the messages in the exact same way. Like a lot of things are the same between them, but some things are a little different. So even though they're using a common message set, they may not use the messages in the same way. So that is something like you have to be aware of. Okay, so now a brief overview of simulation. So simulation is a great way to test your software without having to go and fly it on a real drone. It is quite difficult to fly real drones. It takes a lot of effort to first build a drone, Um, and then you have to like go somewhere where it's like safe. So there's a lot of time investment there. And not only that, you're essentially risking your drone. It could like crash and it's very expensive, costs a lot of time to repair. And also there are safety concerns. So all of these reasons are good reasons to look at simulation. The good thing is that in the open source community, there are a lot of different open source simulators. So on the slide here, I've basically pointed out some of the simulators. There are a lot more than this that are available. So here are some of the typical ones that you'll see. So JMavSim is a very simple like quadcopter simulator that PX4 comes with, and that's basically just a basic one that is easy to get going. There's also JSB Sim, which people typically use to model aerodynamics a lot better. And then there's also Gazebo, which Gazebo is more of a robotic simulator, but it is very helpful for the type of missions that we've done in TAR, because essentially you can interact with the world, you can model actuators, you can model physics, and while it has less aerodynamics and aerodynamics modeling, is more applicable to like the type of missions that you'll be doing with a quadcopter. So Gazebo, it as I mentioned, like excels at robotics simulation. Can simulate actuators. You can also write plugins to simulate various sensors, and it also has a rendering engine, so you can simulate cameras too, which is great for testing like SLAM or computer vision in the loop without having to use a real sensor, essentially. And then also you can simulate collisions with terrain and other obstacles that you can insert into your world. So here's a block diagram of how a gazebo simulation would essentially work. So here is the same reference architecture that I had showed for Autonomy. And so when you run a gazebo simulation, a lot of times what you'll do is you'll take away the module that's in charge of communicating with the hardware, and then in your simulator, you will write a module, or you will use an open source module that publishes the data straight onto the ROS network, which is actually another plus of Gazebo, is it's very highly tied to ROS. So there are a lot of packages that are a lot of pre-made sensors, and then a lot of support for making simulations of sensors that will publish to ROS. And similarly, like we removed the camera driver, and now Gazebo is essentially taking what this driver would do. Another thing worth noting is you could run the almost the exact same Autopilot software in the loop. I wish I had made another block diagram of the Autopilot, because similar things to the Autonomy happen. Let me go back actually to the Autopilot block diagram. So similarly, there's a hardware interface in the Autopilot. And so in Gazebo, you'll have a simulated IMU, simulated gyro, and simulated GPS. So all of these modules essentially are not compiled in the Gazebo CITL target. And basically Gazebo is able to publish the data in the place of these. There's essentially like a different module that takes the place of this, that translates the Gazebo data into the hardware abstraction layer, which then allows the rest of the system to function in the simulator. Yeah, that's a high level overview of how the simulator works, essentially. Okay, I think I'm going to leave it here for now. and we'll go into the intelligent quad simulator. So at the beginning, before we started the presentation, I had mentioned why I had built the intelligent quad simulator, but it essentially is it comes from the time that I'd spent at TAR. Like, we spent so much time trying to dual boot people's PCs because a lot of the software that we use is Linux only, especially on the simulation side. And then once you dual booted your PC, you essentially had to install all these packages using Linux, which I was not familiar with in college, and most people that were in TAR were not familiar with. So it was quite the struggle. Not only that, like the different pieces of software, open source software, are like not like the easiest things to install because they're kind of like half supported. It's like pieces of software that people kind of publish out of their own goodwill. So they don't have like tier 1 support, and it's not guaranteed to work on your system. So the idea is I've essentially done the hard work of creating the simulation infrastructure. And because I'm using a cloud provider, the cloud compute is essentially infinitely scalable. And also, I'm able to create and destroy compute hardware as the demand for the simulator is as it grows and declines. So that makes it very efficient for me to host the simulator. The current simulator is based off of JMAVSim for PX4, and then there is a for Ardupilot, the quadcopter one is a custom simulator that Ardupilot has, and then the planes are JSB Sim, and then I'm not sure what the sub and the rovers are, but essentially it's the basic simulators that come with the different autopilots. And as of now, like, the simulator cannot fully replace Gazebo. I would like to one day. However, there are a lot of challenges with essentially hosting Gazebo in a cloud cluster like this. Like, I've done some prototype systems, but the limitations there are mostly monetary, because Gazebo just requires so much more compute. It is very pricey on my checkbook, essentially. Some of the advantages of my simulator basically are that it requires very minimal setup. It's operating system agnostic, so you can essentially use it on Mac, Windows, or Linux. You can easily switch between PX4 and Ardupilot, as well as versions, and also the different vehicle types, which this was something that I was never really able to do when I was in TAR, because when you like self-host the simulator, it basically requires a rebuild of the Autopilot software every time you change versions, or if you change to a plane, or if you want to switch to PX4, you basically have to learn a whole different like build chain, or I wasn't willing to like put in the time and effort to be able to try things out. But with the simulator, you'll be able to like just try out a bunch of different configurations and just get a better sense of how they operate. As I previously alluded to, there are some limitations. So my simulator doesn't do collisions with obstacles. Like, you can't insert obstacles for it to collide with. In the multi-vehicle simulations, they don't collide with each other. And then there's no rendering engine in the simulator, so you can't simulate cameras or LiDAR or anything like that. But you can test like guidance software, essentially. And here's essentially how the IQ Sim might work in the reference autonomy architecture. So what you'll notice is like you won't be able to test your SLAM, or you won't be able to test vision in loop because there are no simulated cameras or LiDARs for that to run. But you can potentially, test behaviors, different behaviors. You can test MAVROS and some of the other modules that you might have that don't require vision or LiDAR. And I think that is the end of my PowerPoint here. So at this point, I wanted to go ahead and try out the Intelligent Quad Simulator. And I was hoping that y'all would be able to follow along as I'm doing this. So I had sent out an email giving some brief instructions on things to set up. And if you've set those things up, you'll be able to follow along with this demonstration like pretty easily. I will give a bit of a disclaimer. I've never had this many people simultaneously using the simulator. So I really hope things work, and I think they will, but nothing's guaranteed when we're stressing the system like this. So with that disclaimer out of the way, we can go ahead and try it out. So when you log into the Intelligent Quads website and you come to the simulation tab, you'll be greeted with this interface, which basically will allow you to configure your simulation. So you can switch between Ardupilot and PX4. And Antonio was telling me that you guys are probably going to be using PX4. So for the demo, I'll go ahead and use PX4. Right now, there's only the JMAV sim simulation type. And right now, I'm only supporting quadcopter on PX4, but on Ardupilot, you can do copter, rover, plane, and you can do plane or quad plane. And there's a lot more options on the Ardupilot side, just because that's what I'm a little bit more familiar with. And then you can also do multiple vehicles. So if you wanted to do more in the same place, you can increase this number up to 3, is what I have as the limitation. You can also change the location. So there are all these preset locations, but you can also just essentially type in a lat long altitude to go to any custom location. This is something I wish to improve in the future, but this is kind of how it works right now. In addition, you can also mix like vehicle types. So we can have vehicle type 1 that's like PX4, and then we can have a vehicle type 2 that's Ardupilot, and we could even change this to like a plane or a rover or something like that. So I think that's all I really want to talk about for the configuration dashboard. And so let's go ahead and try everybody starting up a simulation. Let's see how well this works.
Vehicle 1 communication lost.
So I'm starting a simulation right now. And so I'll get the simulation ID. And if you download the client, you should be able to take the simulation ID, copy this in, and then you should be able to hit connect.
Vehicle 1 communication regained.
And,
Vehicle 1 disarmed.
Go ahead and
Vehicle 1
close that. Were you guys hearing the QGroundControl audio?
manual flight mode.
I'm gonna.
I don't think it did. Can you try it again?
I'm just gonna go ahead and mute it because it's
Hold flight mode.
It's annoying. I can certainly hear it. Here, mute all audio outputs. So here, we were able to connect to a drone. So I'd like to pause for a second because in my email, I did mention that I don't have a client for macOS. So for the people using macOS, what you need to do is the following. So first of all, there is a documentation page, and then if you go to connecting a GCS, you can go to QGroundControl, and for macOS, you'll need to follow the direct connection instructions. So basically, you'll start the simulation, and then you'll copy the IP address. Then you'll need to come to the application settings, and then you'll go to comms links, and then you'll hit add, and you'll create a new link, and then you'll just name it something, and then you'll click TCP. You'll paste in the IP address, and then you'll paste in the port, and then you'll hit OK. And then you'll hit connect on that link that we just set up, which should give you the same link that the client does. The client's nice because essentially it does that, and then it takes that TCP stream and then makes it into UDP and sends it on 14550. So the longer that you use the open source software, you'll start to notice that this number 14550 is a special number. This is basically the default UDP port that a lot of the different open source MAVlink software is expecting you to be sending out UDP. So basically, QGroundControl will auto connect to your drone when you have MAVlink sending on localhost, or actually just sending to the computer on port 14550. So I'll hit connect again, and we'll get the stream back. So this is actually, before we go on, I just want to pause and ask how things are going in the room. Were people able to make the connections?
Let me check. Wait, who was able to make a connection? Anyone? No one yet? Yeah, I think we might have some issues with connection here, I think.
Okay.
Does it pop up anything on the terminal? Oh, okay. Oh, yeah.
Yeah, I just looked at the dashboard I have set up here, and it seems like I can see a lot of simulations currently created on the server. So it does seem like the server is creating all the simulations. Yeah, just let me know if people are having other issues connecting.
Yeah, we're having some issues, but if you could give us like a few minutes to try to figure them out.
Yeah, sure. Let me know if there's any questions I can help with.
Oh, hey, Eric.
Yeah.
So I remember, I think a while ago, a few months ago when I tried it, there was like a terminal interface. I wonder, is it still there?
A terminal interface, this one?
Yeah, or the one where it had the Python scripts?
Yeah, so I ended up taking that one down just because I really wanted people to use the dashboard, and I'm on a journey as a solo developer, and I kind of wanted to minimize the different features I had in there.
Yeah, that makes sense. Yeah. Also, one quick question. if that's okay.
Sure.
I remember, I think when I tried it with the Python scripts, I know there's some stuff in there that you have to detect the heartbeat of the vehicle.
Sure.
What was that? Is that always necessary?
So for Ardupilot, basically you have to send somebody on your MAVlink network needs to send out a heartbeat in order to initiate Ardupilot to start sending. But on PX4 will automatically start sending the MAVlink data when the application starts.
I see. Okay, that makes sense.
Yeah. So on this side, some people are like pasting in the simulation ID link, but whenever they paste it in, it's not doing anything.
Oh, really?
Yeah.
Oh, interesting. Yeah, if somebody could, copy and paste any error messages into the Slack channel, like I would love to try to address those.
It isn't connecting. Someone else needs to paste it. You might go help me. Okay. So it's not giving like an error. They said that it like is opening up the terminal, and
Okay.
after that,
So it lets us know that the router started with the 4 endpoints, and then it opens those channels, the TCP, UDP,
Okay, so that more or less sounds like it's working. Do you guys also have QGroundControl open?
I opened my ground controller. I don't know what to do with it.
I think it's just supposed to automatically connect to it, right?
Yeah, that's the idea.
Oh, right. For me.
There's no auto connect. Another thing to check is if in QGroundControl, if you go to the application settings here, there are these checkboxes down here, and so you'll want to have the UDP checkbox connected or checked so that it will try to make that automatic connection.
Eric, could you explain also like one more time, like where to get the simulation ID and where to paste it?
Sure. Yeah. So basically, when you hit start, there will be this simulation ID down here, and then you can just hit copy, and then so I'll back up. I had already had my client open, but I have my client downloaded to like my documents folder. So I just double click this app.exe, and then I paste in my simulation ID there, and then I hit connect, and then when I do, the connection is restored. Yeah, it's totally possible that that we might have managed to break the system, but I really feel like it should be working. So this is really sad if it's not.
All right, I'm gonna like walk around and try to help a few people.
Okay.
We got some successful connections on our end here.
Hey.
Yeah.
That's really good news. Okay. Interesting. I'll have to look into I'll have to figure out like why some other people are having issues.
One quick question. So when you start the simulation, should you open Q ground control, so the control station, before connecting to the SIM-ID?
It should be order agnostic. Like it shouldn't matter if QGroundControl is open or closed before.
Okay. Makes sense. Thank you.
Are some people using school computers? Or are most people using their laptop?
Yeah, I think everybody's on their personal, right? Yeah.
Okay.
Yeah.
Yeah, it seems like several people kind of got stuck at the same point where like it just doesn't connect to the Q ground control.
Okay. One thing that might be happening is it could be firewall related rules. So one thing, if you're on Windows, to try is to run as administrator the app.exe. Do you guys know what the distribution of OSs in the room are? Is it mostly Windows or Linux or Mac?
It's mainly Windows.
Mainly Windows. Okay. Was anybody able to have some success doing the run as administrator on Windows?
Not on this side, Eric.
Okay. One other thing to try is to stop your simulation and start it. I potentially know of one bug that might prevent people from connecting when there's a lot of traffic on the site.
Someone asked if the launching with what was it called?
Online visualization.
Online visualization, like beta, if that would work.
Yeah, so the visualizer basically just shows you the position of the drone in 3D space. Yeah, that shouldn't be needed for this demonstration, and it shouldn't help. It wouldn't help.
Thank you.
So I think we should just wait like one more minute, and then I will just continue on with the demonstration, and then we can try to do some debugging a little later if we feel like it.
Sounds good.
Okay. Okay, I think if y'all are okay, I'm just gonna continue with the demonstration, and then we can try to figure out any remaining issues after the fact.
Yeah, the people tried like what you recommended, and they still weren't able to get it to work.
Okay, that's really interesting. Yeah, I'll have to think about that. So, continuing on with the presentation, this is QGroundControl. This is how you can control your drone without using like a RC controller. So over here, there is the command that will allow you to take off. This button will like go into a mission planning mode, so you can make auto missions and upload that to the aircraft. If you go to the vehicle setup, you'll have a bunch of different tabs here. So there are a lot of tabs for setting up your aircraft. So like if you're plugging in a real flight controller, like you could select what type of aircraft you have, and then you could go through all the different sensor calibrations. So you could calibrate your compass, your gyroscope, and other stuff. Here is where you would calibrate your RC radio on a real aircraft. Here is where you can assign different modes to different switches on your RC radio. The power tab basically like allows you to configure some parameters about monitoring your battery. This can help you figure out which motor is which and which direction they're going. This is a pretty crucial tab. So this basically allows you to easily configure your fail-safes. So I know in Ardupilot, actually here in PX4 too, like the fail-safe action for a low battery is just a warning. So I would basically want to set this to either land or return to launch with the battery fail-safe. Like you really don't want to overdraw your LiPo batteries, since if you overdraw them, there's a good chance that they will catch on fire. So this fail-safe right here is very important in my opinion. Another one to consider is, I know in Ardupilot there is a ground control station loss, which usually that one is just worn by default. Setting that one to return mode is good, especially if you're not flying with a RC controller. Here's like another tab that can help you with PID tuning. Another one that can help you with tuning. Some camera, and then here's the main parameter list. So there's a bunch of different tabs, and you can change all kinds of, literally all the features on the aircraft through these parameters. So the EKF has a ton of different parameters, which you can like read about and like look up online. There's lots of documentation, and so this parameters tab is pretty important, and I've used it a lot. Just to like show off the interface to PX4, you can basically, as easy as clicking takeoff and slide to confirm, you can get the aircraft to start flying. So you'll see down here, the up here is showing your altitude, and this like other one is showing your upward velocity, and this one will show your horizontal velocity. And you'll also see voltage and current if you set that up, which you can also, add more tabs here and set up other things to monitor. So you could set up some information on GPS or whatnot and put that in your hotbar so you can keep tabs on it. Sending the drone to different places is really just as easy as clicking on the map and hitting slide to confirm, and the aircraft will go there. There's a couple other actions that become available once you start flying. So there's the actions tab you can click that, and then you can basically change the altitude. Slide to confirm. You'll see the altitude change. The other one that is available is the return to launch feature. So you can slide to confirm, and then the aircraft will fly to a certain altitude and then fly back to the launch position, which is also another big consideration that you should take. There's a parameter in here. I think it's called like RTL something. RTL return out. So this one is a good one to consider, especially if you're going to be flying indoors. You would definitely not want this one to be 30 meters if you fly indoors, because your aircraft will definitely go through the ceiling if RTL is called. And then similarly, like the mission planning is pretty easy. You got to start with a takeoff, and you can adjust the altitude, put it at 5 meters, and you can plop in waypoints. You can even do more complicated stuff like scans. So, like, you know, if you were going to do a survey with your drone, you could plop that in and, you know, adjust the area that we're going to survey. And there's a bunch of parameters that you can play with, but I'll just upload that. And then should be able to just slide to confirm, although it said not ready. Although I think it might go anyways. So and then the aircraft will fly the mission that we just planned, which is pretty cool. So I know that we've had some problems setting up the simulator, but getting to this point in the past has been a heck of a lot harder than what we just did. And assuming that the cloud simulator works, you know, this could be a very valuable tool, especially for people who aren't necessarily directly involved with writing the software, because you can come in here and you know, just figure out how the different features in the Autopilot and ground control software works, so you can get a better sense of how the system operates. I hope that is evident now that you see it. So with that, I'm just going to stop my simulation, just start a new one, which actually I'm going to go back to PX4. Very interesting. Okay. I think we're gonna get Ardupilot. I'm gonna close the GCS. I think we're gonna get PX4. I mean, because when I refreshed it, reset that back to Ardupilot, but I think I'd already hit start. So hold up. So I might be seeing the same issue that you guys are seeing, huh?
Yeah.
So that's really interesting. Like I said before, I've never had this much concurrent traffic on the site, so I guess it doesn't necessarily surprise me that there are new bugs for me to figure out. So let's try this one more time. Let's see if I can get it to go. try it with Ardupilot real quick, just to see if it makes any difference. Well, this is a little bit of a bummer. I really wish we had not broken the simulation today. But that might be the way that the cookie crumbles.
Yeah. It's a problem with connection on our end as well with like getting connected to PGC.
You're having issues? Is that what you said?
Yeah, yeah. Some people and myself included were having some issues just getting it connected to QGroundControl.
Yep. Yeah. I think I'm seeing the same thing.
Yeah, it might be just because I think a lot of people might be on it. I don't know if that may be the case.
Yeah. There's definitely a bug in the website that has been revealed here. Which I will definitely work to resolve. Let's see if I can do a direct connection. I'm wondering if that'll help.
Oh, another thing is, I had another quick question
Sure.
about the different autopilots
Sure.
that I used to. So I know Ardupilot and PX4, they have different licenses. And I was just wondering, I think PX4 is more kind of, there's a lot of resources in each, but I think Ardupilot, like you can modify it a little bit more. But I guess what's the differences in the licenses?
Yeah, sure. So basically, the PX4 license is a little bit more permissive. So basically, you can essentially take the open source project and make it closed source, which on the Ardupilot side, you cannot. So if you make modifications to the flight controls in Ardupilot, the license requires that you at least publish your changes to a public repository so that other people can access it. Yeah, and that's basically the main difference. The features are pretty similar in terms of capability. My feeling is that Ardupilot is a little bit more stable. Like it feels like the user base is a little bit more hobbyists and people who use the drones for mapping and inspections, whereas PX4 seems to have like a little bit more of a researchy base. So like a lot of the features are, things that people create in labs just to like test stuff. And it just seems like some of the features, because of that, are a little less tested and a little bit more buggy. But granted, they usually have features a little quicker than Ardupilot, so there's the pros and the cons. All right, let's try one more time with the with this. Otherwise, might just give up and show a YouTube video. And then we'll end it.
I think they can also like try it out on their own time when
Yep.
there's less people on the crowd.
All right, so I think I'm just going to show a 3-minute YouTube video, and then we can just do questions and answers.
Welcome to the Intelligent.
So this video here basically shows how you can do application development. So it should be as easy as configuring your simulation, taking the sim ID, and then pasting it into the client. You can hit connect, and then QGroundControl will be connected. The cool thing about the client is it allows you to split the MAVlink streams. So QGroundControl will communicate on port 14550, and I've written all the IQ MAVlink tutorial scripts to use 14551, so it's a non-conflicting port, and you can use that port for your applications essentially. And so, you know, I have this little script that commands all the drones, tells them to go to an altitude, and then you know, it uses a little algorithm to make a circle. So based off of the number of vehicles, it'll calculate which or like where to put the waypoints to make a circle, which I only have 3 aircraft, so it just makes kind of like a triangle shape. But once I get this bug that we have discovered with the website fixed, you know, y'all should be able to do the same. And with that, I think we can conclude my presentation, and I can also field some questions and answers right now.
Someone asked what's like the main reasons to use Ardupilot over PX4 or vice versa.
Yeah, I mean, the reasons are, as I just stated, like, yeah, I can't really, I honestly, like, I think the stacks are pretty comparable, and I can't recommend one over the other. I would just like look at the hardware that you want to use, and then you know, see if the hardware is supported in PX4, use PX4. If the hardware is supported in Ardupilot, then probably use Ardupilot. You know, and if there are specific features in the Autopilot, like sometimes those will be implemented in one versus the other. Yeah, and just make sure those features are implemented, the ones that you want. It is pretty easy to switch between the two, so you can also, you know, just try out both. That would actually probably be my recommendation.
Software. So I was wondering like what like the interview process was like, if it was like CS like ish, if it involved like leak code and stuff like that.
For like his position?
Yeah, because he said like he was, even though he was an aerospace engineer, like he went into like software. So I was wondering if that involved like leak code and like CS ish stuff.
Yeah. Did you hear that question, Eric?
Yep, I did hear the question. So for my specific role, the interview process did not, you know, require leak code questions or actually like any technical programming interview. It was mostly just conversations based off of the experiences that I had in the past, and because like I had been part of TAR, the recruiter that I was talking to, I had already showed off like all of the different projects and the things that I had worked on at TAR, and so they were basically like ready to hire, you know, that day, or like with very little like vetting, I guess, or very little like additional vetting. I will also say that like if you go into a field that is less CS focused, so if you go into like aerospace, which is like a combination of computer science and you know, traditional physics and aerodynamics and all that stuff, the requirements, the required like skill level for software is lower, just because you need a knowledge base that both encompasses software, but also encompasses you know, some other traditional aerospace skills.
I guess I am curious about like, I guess how like some of the skills from TAR like transferred over to like your current position.
Yeah, sure. So yeah, I mean, TAR really helped me a lot because I've worked on a lot of different unmanned aerial systems, and a lot of the stuff that we were like working on at TAR like was architected similarly. Obviously, like It was a little bit more. It was a lot more crude than stuff you'll find in industry, since people work on those pieces of software like every single day for 40 hours a week, and there's a lot more people like working on this stuff. But the architecture with the flight control computer and the companion computer, but or at least at Bell, like we'll call it the VMC, the vehicle management computer, and the ground control station, like that architecture is like all the same. Like at Bell, like we use closed source like control laws and closed source like simulation, but like a lot of the patterns are really still the same. But yeah, I mean, you can also like find yourself in situations where a lot of like the same technology is actually just being used. So like the new project that I am working on now is actually using ROS2 and also PX4. So like it's literally the same stuff. There's a good chance that you'll end up using literally the same stuff if you go into the drone industry.
I guess, can you talk a little bit about like how in simulations communication between like multiple drones is handled?
Yeah, sure. So let me go back to the presentation real quick. So I guess so actually I guess in this video, like I'd shown like multiple aircraft, and so the way that this is working is each aircraft is being spooled up with a unique system ID. So there's a parameter both in PX4 and in Ardupilot that controls the system ID of the aircraft, which basically the system ID is supposed to denote a unique aircraft. So if you have a network where everybody is communicating MAVlink, typically like the first drone will be system ID 1, and then you'll have to stagger all the other drone system IDs so that you can know who is sending what, and we can figure out what system ID to send messages to. Does that answer the question, or are there other specific questions?
I think that answered the question. I guess in like a project that I'm working on,
Mm-hmm.
like the drones had to be like in line of sight of each other.
Okay.
So I was wondering if like, I guess some simulations like take that into account, and if like maybe you can like put an object between them to like obstrude the communication between like the two drones.
Yeah. I don't know any like off-the-shelf ways to do it. One thing that like you could look into is, especially if you're simulating this in Gazebo, is you could look into this program called Traffic Control. It's TC. It's a Linux program. So yeah, this traffic control program basically like allows you to inject packet loss as well as block communications, UDP and TCP communications. So one thing you could do is you could write like a plugin for Gazebo that's calculating the distance between all the drones, and like the farther you get away, like you could change the traffic control rule to like inject more loss, and then if you get past like a certain distance, you could maybe like use traffic control to like cut off the entire like link. Another thing to note about traffic control is like the options are like pretty complicated, but I would recommend like asking ChatGPT like how to use it, because I'm sure it could probably crush it.
All right, awesome. Yeah, no, this looks. I'll definitely look into it. Thank you.
Yeah. Are there any other questions?
I think we lost Andres. So I'm gonna see if we can get him back and see if he has any questions.
Okay. Yep. How was Austin wild last night after the Alabama win?
Okay, it seems like hardware just headed out. They
Okay.
sent a message in the chat. Well, I think that's all the questions we had. I guess, are you free to like message on Slack like some of the members if they have questions?
Yeah. Feel free to message me directly on Slack or to tag me in any posts, and I'll try to help you guys as much as I can.
Yeah, awesome. And then if y'all like try to run the simulation on your own and run into any like errors, I guess like send them Eric's way, so you can work on those. So yeah, thank you for coming out, Eric, and giving a presentation. It was very helpful.
Yeah, I really appreciate the opportunity. So yeah, like I said before, I really want to help you guys in any way I can. Yeah, thanks for having me out.
Awesome. And you were recording, right? So like it'll be on YouTube.
Yeah, I'll try to post this later today.
Awesome. Thank you. Well, I think that's everything. So have a good day, Eric.
Yeah, you too. All right,
See ya.
bye-bye.